let's go ahead and finish chapter 1. Put it in the books. Modeling of functions, like I said, this is all about taking the stuff that we've been doing and just applying it to the real world. First one says, how many rotations does a 15-inch, and that's its radius, tire make per second on an SUV traveling 70 miles per hour? This is good old unit conversion. That's all it is. Unit conversion, unit cancellation. You do this a lot in science. And here we are going to do it in math. He says he hates it. Don't worry, it's not that bad. What we are doing is we are going to be trying to turn miles per hour into rotations per second. Hey, look, somebody's printing in my printer. So that's our goal. Change miles per hour to rotations per second.
Couldn't you just find out how many seconds it would take to go 70 miles per hour?
I'm
So
sorry?
in 1 hour, how many seconds that would take? And then just divide that number by 15.
I think that will be the general process of what's going to happen, is changing the miles per hour, and then, like you said, dividing by 15.
So you multiply 70 by 60 squared and then divide that answer by 15.
I think you're trying to jump straight to the answer, though.
Yeah.
Alrighty. Well, I'm going to show all the work. So what did I do first? The first thing I did is I changed my time into seconds, because we're talking about rotations per second. So we say, all right, we got 70 miles. Did I do time first? Yeah. 70 miles per 1 hour. 70 miles per 1 hour. And I went ahead and I converted to seconds first. We do that by saying how many minutes are there in an hour. There are
60.
in 1 hour, 60 minutes. And because we have hours on the top and bottom, this allows us to cancel hours. We now have miles per minute. And you pull off the same trick to get it down into seconds. And then we'll have miles per second. In 1 minute, there are 60 seconds. We switch colors for canceling. There we go. Now we have miles per second. Of course, I don't know an actual number, but we have miles per second. We were trying to find rotations per second. So we're getting there, right? We're getting there. Now what we need to do is figure out how we're going to turn our distance, miles, into rotations. Well, the radius of the tire is given to us in inches. So really what we're going to need to do is first convert our miles into inches. It's a lot of inches in a mile, but let's see. What do we know? We know in 1 mile, and since I'm trying to cancel miles now, got to put it on the bottom. In 1 mile, there are 5,280 inches. Feet, yes, that is exactly what I meant. There we go. It's a good thing people here check me. 5,280 feet. And what have we done? We have canceled miles now.
There are 63,360 inches.
That's a lot of inches. 63,000 and
Yes.
change? Yikes. And then what do we have? 12 inches per 1 foot. Did I do orange yet? I did not. Feet, great. Now what we have to do is talk about rotations. What does it mean for it to be a rotation? Well, right now we have inches per second. And that 15-inch radius tells us that when we go all the way around one time, one rotation, clearly we have used some distance, right? So if you can imagine the circle is the tire and you can cut it and lay it flat, if we can figure out its distance, its straight distance, then we can convert these inches into rotations. Well, what I'm talking about when I'm talking about the circles outside is its circumference, right? Yeah. So we have to figure out the circumference of the circle, and circumference is 2 pi r. Our r is 15. So what we're going to say is that's one rotation. One rotation, one rotation, and 2 pi r, 2 pi 15 inches. And we have now, what color haven't I not used yet? I haven't used fuchsia. We have now converted 70 miles per hour into rotations per second, because rotations is the only unit left on top, and seconds is the only one left on bottom. You would grab handy dandy calculator, because I am not trying to do that kind of math. And just make sure you're really careful about what's on top and what's on bottom with your multiplications and your divisions. You should get about 13.07 rotations per second. Unit conversion. Not too bad, right? Who printed what to my printer? Exponents of scientific notation. Oh joy, look at all this MCR printed to my printer. One of the teachers I share a cart with teaches MCR, and her students don't check which printer it's printing to. And since my room number is smaller than hers, it defaults to my printer, unfortunately. What do you think? Unit conversion easy enough? Been doing this for a long time, right? I think you have. Both in math and science. Let's form some functions from formulas. Now, we kind of already did this when we were doing the composition stuff. Remember we were talking about the angioplasty balloon? You guys remember that? We had the volume of the sphere, and what we did is we solved for its, what's the word I'm looking for? It's R. We solved for its radius. It's that same kind of stuff. It says write the area of a circle as a function of its, well, the first one's radius. How about that? Well, that one's easy. That's just area of a circle. Area equals pi r squared. Very simple. Now for part B, we've been asked to find the area of our circle in terms of the diameter. Well, diameter is 2 radius, right? Every diameter is 2 radii. So what I could do is I could solve for radii here, I could solve for r, and I could substitute it in to pi r squared. So if you divide both sides by 2, you get that the radius is d over 2, and I'm going to plug that d over 2 in right here. And that'll give us the area of a circle in terms of its diameter, in case you ever needed it. I mean, I don't know why you would, but, you know, just in case. Pi r squared. And you might as well go ahead and square that fraction. Let's give you d squared over 4. Pi d squared over 4. Or pi over 4d squared, whatever. You know, pi is the top of the fraction, 4 is the bottom of the fraction. And the last one would be, and I don't know why you would ever want a formula for this, but just in case you did, if I gave you the circumference, could you tell me the area? You could. I think that most of us would probably just take the circumference, solve for the radius, and then plug that number in. But in case you wanted a function for it, circumference is, which we just did, 2 pi r. So again, if we solve for r, we can take what we find for r and plug it into the original area formula. C over 2 pi, because we're dividing both sides by 2 pi. And we can plug that in right here again. Area is, we have pi times c over 2 pi squared. So it gives us c squared over 4 pi squared. You have to square the pi also. So that area is c squared. And I'm going to go ahead and throw the pi on the top of the fraction over 4 pi squared. And I did that so that I could see that it is going to cancel at least one of the pi's off the top and bottom. So this pi cancels one of the 2 pi's on the bottom, so I'll just get rid of the exponent. The area of a circle can be represented as the circumference squared divided by 4 pi. Neat.
I'm confused. Why did you unsquare the pi on the bottom?
Well, I didn't unsquare it. What I did was I canceled one of the pi's off the top and the bottom. It's almost like you had, imagine you had 3 over 9, you know, something over itself squared. So imagine that pi squared down there actually says pi times pi. So I had a pi on the top cancel one of the two pi's off the bottom.
But how did you get a pi on the top?
The pi on the top is coming from right here, this pi that's outside. Because you can call that a pi over 1. I could have done the same thing here, because I could have written this answer as pi over 4 times d squared. You know, just manipulating it. That pi, since it is not a denominator of a fraction, it's automatically a numerator of the fraction. Cool thing? Cool beans? Yes, Ms. Rim. Okay, great. Everybody's got cool beans. I like it. Oh, fun. This is one of those classic algebra questions. A square of side x inches is cut out of each corner of an 8-inch by 15-inch piece of cardboard, and the sides are folded up to form an open-topped box. You know what would have made this question a lot easier before I even read it? A picture. Go gadget geometry skills. We're going to go ahead and draw exactly what it's saying. So we started off with a piece of cardboard. You know what? I'll make it brown because cardboard's usually brown. Let's see. Picture not drawn to scale because I'm not an artist. But here we have a piece of cardboard. And we said this cardboard is 15 by 8. Like so. Now a machine comes around and it stamps a square of unknown size out of each corner. Let's see. That's squarish. Got less and less squares we went, but you get the idea. So we have stamped a square off of each corner. What we know is that square is an x by x square. X here, x here, x here, x here. Got a little cramped over there. Those have all been stamped out. And the result is that you could fold the sides up now and create an open topped box. Here's the geometry skills. You ready for this? Be amazed. Ta-da! And oh, you ready? Ready for this? Let's see. Trying to remember how to do this now. There. Now it's as if you're looking down inside the open top box. There. Impressive, right? I know. You guys are so lucky. The one thing we know right now is that when you folded this bad boy up, this and this became, say, this one right here. They're going to touch right there. So we know then that this box's height is the side length of the square. It's x. We know that. Now part A says something about volume. So we know we're going to be dealing with the volume of a box, right? That means I need to know its length and its width. Well, this side down here was 15. But after I stamp my squares out, what's left?
15 minus x squared.
Close.
2x.
2x. This is because we removed an x here and we removed an x here. So it's 15 minus 2x. And then the last one would be, what color have I not used yet? Equal opportunity color user here. This one was 8. And again, stamped 2 x's out of it. So that's going to give me 8 minus 2x. That's this. I should have finished color coding. There we go. Part A, we haven't even started the question yet. Part A, write the volume of the box as a function of x. All right, well, the volume of the box is length times width times height, right? I'm going to run out of space, so I will have to give myself a little bit more of it here. Catch up with the active panel. There we go. A, volume is length times width times height. Which one you call length and which one you call width? Unimportant. The height, though, I'd say the height is x.
It's multiplication, so regardless of the order, you'll get the same answer.
Exactly. Multiplication doesn't care about the order. That's always nice. There you go. Length times width times height. We weren't asked to FOIL or anything. It just said just to write an expression. There you go. That's good enough. It's weird seeing that x at the end. You can move it to the front if you want, but it really doesn't matter. Part B says find the domain. Huh. Well, you know what? We don't need to actually graph this thing to talk about its domain. This, let's just say this is a real box, right? This is a real box. What is the absolute smallest value that x, and I'm talking this one here, what's the absolute smallest value that x could approach?
1.
0 even. Now, because it's a real world box, this thing, now McKinley said 1 because she was thinking, well, there's no way the box is, you know, yay tall, but it could be. It could be an inch tall. It could be a ½ inch tall. That wouldn't be in a very effective box. But the point is it would still be a box. But we do know that 0 is the bottom of the domain. Can x be equal to 0?
No, because then it won't have anything cut out.
Right, because if x is 0, you haven't cut anything out, there's nothing to fold. So what we know is that our domain begins at 0, but we need to know what its absolute maximum is, and yes, it does have an absolute maximum. How do you think we could figure out this max value of x?
8?
Well, let's see, I got a couple hands. They want to. You're trying to tell me what the answer is. Why can't this thing see me? Come on, Cameron. All right, Brooks, what do you have for me? I'm looking for how you think you would find. Yeah? Right, he says take one of the sides, set it to 0, and solve for x. Now the question is, which side? Which side determines the volume for me, or the domain for me, Tag? The 15 side? Agreed? They neither agree nor disagree. Does that mean nobody knows? That's what that means? Okay, so she says yes, that's what that means. Let me ask you a question. What's more restrictive? The big side or the small side? The small side. You're going to run out of space on that side before you run out of space on the big side. So yes, the idea is take one of the two sides, set it equals 0, and solve for x, but you have to use the more restrictive side, just like when we were trying to do domains of composition, stuff like that. You're looking for the more restrictive. So the upper bound of our domain is decided by the smaller side. So 8 minus 2x equal to 0. So 4 is the absolute maximum x could be. And if you did cut out a square of side length 4, you would again not have a box. So we can't actually get to 4. Our domain exists between 0 and 4. Now part C and D, those are calculator questions. So I'm firing up handy dandy TI, and we will do this on our graphing calculators. If you don't have a graphing calculator yet, remember you could always use Desmos, and that would be the strong suggestion, use Desmos. I'm going to be honest with you, what we're about to do is even easier to do on Desmos than it is to do on the graphing calculator, but I need to teach you how to use the graphing calculators. Yes, sir. So how do we get out of parametric mode? Press the mode button, and then just scroll down and highlight function and hit enter. That gets you back into y equals mode. Good? You're very welcome. All right, let's see.
Wait, how do I get out of the x equals mode thing? T.
You're right here. You're going to, actually, let me quit what I'm looking at. You're going to click on mode, this top button right next to second, and you need to scroll down here and highlight the word function and hit enter. And that'll get you back into y equals mode. All right, let's see. Y equals, well, look at that crap. Let me clear that off. What do we have? We have x times 15 minus 2x, and then 8 minus 2x. click on mode, and then go down to function.
Hey, where's mode again?
Right next to the second key at the top. So now you guys could see that there was already stuff on my calculator. That's because I used the same calculator program for all of my preps, right? There's a really good chance that I graphed something in one of my other classes and it's not going to have a really good scale for me. So just out of habit, before I hit the graph button, I always hit zoom 6. That's just habit. I just go ahead and do it. There. Now what we have here is clearly some kind of cubic, right? Because we had an x outside and then 2 parentheses with x's in them. Well. Now we want to pay attention to our domain. We said that we could only exist between 0 and 4. That's on the x-axis. Now we're looking for a, what did it say? It says graph v is a function of x over the domain you found, so 0 to 4, and use the max value finder of your graphing calculator to determine the maximum volume. Well, I don't see the top of this function. It's up here somewhere, up in space. I actually have no idea what that number is. I'm going to take an educated guess. This thing looks really steep, and I'm going to take my y values from 0 to 100, and I'm going to hope. I honestly don't know. So window, my x minimum is 0, and my x maximum is 4. We know that. My x scale, whatever, it can go by ones, who cares. Y minimum, it's a volume, so the minimum value that you can approach is 0. And I'm taking a total stab in the dark with this maximum, and I'm hoping that 100 is big enough. And I'll just say y scale is 5, so it'll give me 20 tick marks from top to bottom. And graph, and hope. That was a pretty good guess, actually. I swear to you, it's not written on my paper. Total guess. Our maximum value is going to happen somewhere around right here. Part C says, determine the maximum volume. So it wants to know what that max volume is. Is that an X or a Y?
Wait, wasn't there more on the other side of it? Even further to the right as
There
well?
was more to the right, McKinley, you're right. But remember, this function that we wrote is just math. But we know that it represents an actual object, so the maximum value that X could actually be is 4. I'm going to hit zoom 6 real quick just to show you what I'm talking about. So right here, we see that the function dips below the x-axis, right? So between this x value and this x value, we're being told we have negative volumes, which is an impossibility. And then over here, your volume shoots up to infinity, which again is an impossibility. So we are restricted by the 0 to 4 domain. Sorry, just retyping this real quick. Regraphing. All right. And now I get to remind you, because I'm pretty sure I already showed you, but we're going to remind you how to find a maximum value on your graphing calculator. If this was Desmos, you legitimately would just click on the curve and it would give you the answer. But anyway, like I was asking, when it says what's the maximum volume, am I looking for an X or a Y? A Y value. The next question says, how big should the cutout be in order to get there? That's the X. So once we find this maximum value, Y is the answer for C and X is the answer for D. To find your maximum, you go to second trace, which is the calculate menu, second trace. And then maximum is the number 4. Second trace max. Boink. Remember, the calculator is going to ask you some questions, and right now it's saying, hey, am I to the left of your answer? You can see the cursor's clearly not, so you just click left until you get to the left of the answer.
How did you get that?
Do second, then trace, which is the key up at the top, and then maximum. Now, I've just gone generally to the left of where the answer really is. I don't have to be too precise about this. It just has to be to the left. And then now I need to go to the right of the answer. Again, you don't have to be too precise. Just make sure you go to the right a little bit. And then when you're taking a guess, you just make sure you're in between the 2 dotted lines that your calculator just created for you. As long as you're in between them, you'll be just fine. And then you hit enter. Now remember, part C was asking for what is the maximum volume. The maximum volume is right here. It's second trace, not just trace. If you do just trace, it'll allow you to move along the curve, but it'll never be exact answers. You have to do second trace to get exact. So our maximum volume is around 90.74. And it happens when the squares are 1.6 repeating inches long. That's what that's showing us. So that answers part C and part D. Part C, max volume is equal to, what was it, 90.74? 90.74 cubic inches. And that happens when x equals 1.6 repeating inches. Ta-da.
Wait, there's 6 6s, then 1 7.
That's only because the calculator can't show you all the 6s because it's not programmed to have the 6 with a bar over it. So what it did is it rounded that last 6 to a 7.
Oh, okay.
You would think that, I mean, expensive piece of technology, you'd think they'd be able to tell it like, yeah, 6 with a bar over it. But you would think so, but it doesn't. But yeah, that's what it does.
It's just a bar.
Yeah, when the decimal either repeats or is irrational and goes on forever with no pattern, it will reach a point where it can't write any more numbers and it'll just round the last number. But since we can see it's obviously a 6 repeating, there you go. Fun question? It's not that bad, right? It's a classic algebra question.
If there was a 7, it just ended with the 7 and wasn't repeating. So
Right.
that is good to know.
Yes, tag. Wants to know if we'll be using the graphing calculator on the test. No, we won't. So maybe you're wondering why I have this question then. Well, one, I need you to know how to use a graphing calculator, but two, the concept could still be on the test. The concept is, could you find an equation and tell me a maximum value? Do you know how to find maximum values on cubics? No, not yet. I'll teach you at the end of the year with some calculus. But you do know how to find the maximum value of a quadratic, right? It would be at its vertex. So the concept could still be on the test, but you will not have access to a graphing calculator on the test. I will tell you this though, the LEOC at the end of the year, you will be allowed to use your graphing calculator on it, which means that thing should be redonkulously easy for you, as long as they didn't change the test. The calculator won't solve for you, but it does graph a lot of stuff for you, and a lot of the answers can be found simply by graphing, if you know how to use your graphing technology. Oh boy, now we're going to protect an antenna. This question's fun. A small satellite dish is packaged with a cardboard cylinder inside it for protection. The parabolic dish is 24 inches in diameter and 6 inches deep. Okay, my picture doesn't show that, so I'm going to go ahead and write that on there. Diameter goes from side to side, so I've got this going on. 24. And since everything's in inches, I'm not going to bother writing the inches. And 6 deep. 6. There. The diameter of the cardboard is 12. How tall must the cylinder be to fit in the middle of the dish and be flush with the top of the dish? And you're looking at that and you're thinking, holy cow, there's no way I have enough information to answer this question. Oh, but you do. Oh, but you do. How? Well, the way we do it is we pretend that this figure is on an XY plane. Where on the XY plane? Wherever you want it to be, that's the answer. So wherever is most convenient to you. 0, 0 is the most convenient place to put this thing. So what I'm going to do is I'm going to, and I'll do it as a dotted line, I'm going to be putting a dotted XY plane so this would be my X's and this would be my Y's. Why would I want to do that? Because if I do that, then I know coordinates of things. I had a coordinate right here, but my paper has a hole punch in it, and wouldn't you believe that half of it's missing? That's okay. We're smart people. We can figure it out. And we'll also get a coordinate here. Let's do the one with my hole punch on it first. the far right point. The coordinate of that far right blue dot. Well, let's see. I used 0, 0. This thing is a parabola, so it's symmetric. The diameter is 24. What is the x value of that blue dot? 12. Good. And what is the y value of this blue dot? It is 6, because that is the height of the parabolic dish. So 12, 6, or the depth, I should say, 12, 6. Awesome. And the orange dot, again, symmetric. So what is the x value there? 6. And what's its y value? No, the y value of this coordinate. So 12, 6, because it's got to be flush with the top. It's supposed to be 6, 6. Go home, McCutcheon, you're drunk. 6, 6. There we go. Yay, I'm smart. Okay, what do we got going on? Well, we're talking about modeling with functions, right? We should probably write a function. How about a function for the parabola? How about that? It's centered at the origin because we made it be like that, so life is good. Because when you write it in vertex form, it doesn't have the h or k in vertex form. So rather than write it like this, rather than write it as some number x minus h quantity squared plus k, we know that h and k are both 0 because of where we place this thing. So the function right now is really just ax squared. And the a would represent a vertical stretch or shrink. How do you think we solve for that number? Because we need it. How do you think we find it? Yeah, what do you got? Which point? Yes. Ashley says to plug in 12, 6. Absolutely. 12, 6 is one of the coordinates we know exists on this parabola. Just be careful. 12 is your x, 6 is your y. So we have 6 equals a times 12 squared. It would be great if you knew what 12 squared is, but it doesn't work. Don't worry about it. You have a calculator on the test. We get 144. Not everybody knows that. Let's see. And I'm too lazy to put the 144 in front of the a, but you're going to divide both sides by 144. And reduce your fraction. Let's see. Can I divide this by 6? I can. It would be 1 over something.
24.
24, thank you. 1 over 24. So our equation is y equals 1/24 x squared. And you might be wondering how this has helped you. Well, remember that that cardboard tube is touching the parabolic dish. Right there. Our job is to figure out how tall the cylinder must be. So we're actually looking for this value right there. That's what we're hunting for. But for that fuchsia point that I just put on there, what is its x coordinate? It's 6. Yeah, it's a rectangle on slice. So it's going to be 6 comma some unknown y value. And once we know that y value, we'll know the top of the tube is at 6 and the bottom of the tube is at whatever that y is, and we simply subtract. And that'll tell us the height of the tube. So we plug in the, what's that? Yeah, it's exactly what you do. You put in 6 for the x. So y equals 1 over 24 times 6 squared, which is 36. 36 over 24. Reduce your fraction. 12 goes into both of these. 3 over 2, which is 1.5. This y value right here is 1.5. So the height of our cylinder is just 6 minus 1.5. Which is 4.5. So as long as that cylinder is 4.5 inches tall, it'll sit right in the bottom of the parabolic dish, and it'll be flush with the top of the parabolic dish. Isn't that fun?
Fun.
Yes, fun. I said the word fun. It's one of the only F words you're allowed to use in my class. Fun.
No.
Luckily, it's the F word I use most often when I'm talking about mathematics. Most often,
I think
yes.
most of us use a different one.
Most often, I say fun. Grain is leaking through a hole in a storage bin at a constant rate of 8 cubic inches per minute. The grain forms a cone-shaped pile on the ground below, and I drew a cone for you so you wouldn't have to try. As it grows, the height of the cone always remains equal to its radius. Oh, they just gave us some valuable information. The height equals the radius. Well, I mean, let's throw it on the picture, right? The radius, since we know we're going to be working in function land, you might as well use an x instead of an r. And you've been told that its height is always equal to the radius. If the cone is 1 foot tall now, how tall will it be in 1 hour? And then I gave you the equation for volume of a cone, 1/3 pi r squared h. Okay. Got to be a little careful though, because the question was given to you in 8 cubic inches per minute, but then you're told that the cone is 1 foot tall right now. Those units don't match. So what we're going to do is we're going to remember that 1 foot tall is 12 inches. Let's start there. Okay. Got to make sure that you're always in the same units. We know that volume is 1/3 pi r squared h. So right now, when our cone is 1 foot or 12 inches tall, our volume is 1/3 pi, the radius 12 squared, and the height is always equal to the radius. So it's 12 again.
Wouldn't it be easier because the height and the radius are the same thing? To make it volume equals 1/3 pi r cubed.
Yep.
Because it's the exact same thing.
There you go. It'll be the exact same thing. And the way that we've done it's actually 1/3 pi x cubed, right? But yep.
Yeah. But still.
So this is going to give you, when you type it on a calculator, 576 pi. We want to have the pi there because it's an exact answer, 576 pi. Great. So we know that right now it's 576 pi when it is exactly 1 foot tall. It wants to know how tall it will be in 1 hour. Well, the volume goes up by 8 cubic inches per minute. So volume increases by 8 cubic inches per minute. We're talking about 1 hour from now. So that's how much it increases. In mathematics, how do you generally increase a number?
Multiply it.
Well, multiplication, yes, but typically if I just want to increase something quickly, you could just add. So technical multiplication is a type of addition, technically. So what we're saying is our volume in 1 hour will be the 576 pi that it is right now, plus the 8 cubic inches that is growing per minute, and we know we have 60 minutes in an hour.
Also, just add another 60 minutes to also figure out how many there are added on. Like, so
What's the question?
576 pi, and then we add another 60 minutes worth of stuff.
Well, right now the volume of the cone, is 576 pi, and we are adding another 60 minutes worth of volume increasing. Yep, and it increases at 8 cubic inches per minute. This gives us 576 pi plus 480. Great. We now know what the volume is going to be in an hour. And it wants to know how tall it will be. Oh. Well, its height is x, right? And like McKinley told us a second ago, this is volume is 1/3 pi x cubed. So we know that that 576 pi plus 480, that is my 1/3 pi x cubed. And that's how I can solve for x. I'm running out of space. 576 pi plus 480 equals, where'd it go? 1/3 pi x cubed. Cancel fractions, and you know what? You know what would make life even easier? Instead of calling it 1/3 pi, why don't you call it pi over 3? Come on, catch up with me, panel. Is it gonna work? Ah, look, it's crashing. Yay!
It crashed.
Don't worry, it came back. It decided it was gonna continue working today. Let's call it pi thirds x
For
cubed.
now.
Great. Now, how do we cancel all fractions?
Multiply by its reciprocal.
The denominator is half of the step, but then the other step would be to divide by the numerator, so we're going to multiply by the reciprocal. If you want to do it in 2 different steps, you're welcome to. You'll always get the same answer, but it's faster just to multiply both sides by the reciprocal of 3 over pi. That'll cancel it on the right side. And on the left side, we're going to get 576 pi plus 480 . And I'm not going to actually figure out what this number is because it's not really worth our time. Because this is a calculator question. All you have to do now is get x by itself. Cube root. Cube root of both sides, and I'm going to show you how to do the cube root on your graphing calculator right now. And the cube root can be done on a scientific calculator as well, and it's done pretty much the same way. Now the graphing calculator makes life a little bit easier, but I'm just going to go ahead and tell you the answer. Actually, you know what? I have time. I can do it on the graphing calculator. Now, just in case the bell rings. That is going to be 12.98 inches. About 12.98 inches is going to be our answer. But I want to show you that on technology. Hopefully you know how to find a cube root on a scientific. Yes? No? Maybe so? You guys know how to do that? No one's saying anything? Yeah, on that one. Or even the better version of that one, but yeah. All right, let's see. Cube root. You know, if you don't know how to do cube root, you could always just do raised to the 1/3 power, right? This calculator does have an x root. I just have to find it. Where is it? It's hiding from me. Wonder if it's in math. Yep, there it is. Math. And it has a cube root function. And we have some kind of ridiculous fraction on our hands. So math, frac, n over d. 3 parentheses, 5, 7, 6, second pi, which is on top of the caret, plus 480, close your parentheses, and on the bottom we have another pi. There we are. Much easier to do on the graphing calculator. 12.98, and there you have it. Sure, of course I can do it one more time.